All right, guys, we're starting a new chapter. Isn't this exciting? I'm excited. Um, so this section today, we are going to talk about trigonometric identities. So an identity is a statement in mathematics that is true, right? So it's an equation that is true for all possible replacements of the variables. So, you've already dealt with identities in your mathematical career so far. A squared plus b squared equals c squared for a right triangle, right? That is an identity because as long as that a and b are legs of a right triangle, and c is the hypotenuse, then that will always be a true statement. So identities are really important. Mathematicians really like identities. We like finding these true statements that we're allowed to come back to and we use them to solve problems. So the identities that we're going to do in these next few sections are really important. And a lot of times I think you're going to be feeling, when you simplify some of these, what is the point? And you might be feeling that in a lot of ways. But as you go on in your math career, so when you get to calculus, when you get to differential equations, if you're able to see an expression or an equation and know how to change it or to manipulate it to do something that is maybe makes things a little bit more easier, makes you able to actually solve the problem, that's always a good thing. That's going to be our goal here. So be patient with this stuff. Take time with this stuff. The way you get to know these, write them down a bunch of times, use them, do a lot of example problems. That's true for any subject in mathematics, but that's especially going to be true for these identities that we're going to do. Make flashcards. You're going to have to memorize these identities and you're going to need to know them. So you need to figure out a way to memorize them. So let's first kind of write down some of the basic trig identities that are going to be important as we move on. And some of these you may know already. Some of these you may have kind of guessed as we've been dealing with these trig functions. And of course, some of them are pretty obvious in how we define certain things. So first of all, sine of x, cosecant, and sine, right, are just reciprocals of each other. So two of the identities that we have that deal with cosecant and with sine are that sine is 1 over cosecant, and cosecant is 1 over sine. That's just true because they're reciprocal functions of each other. Okay, so that's going to be kind of my first line that has to do with sine. There's one other identity that has to do with sine that's important, and that's this idea that sine is an odd function, meaning if I take the sine of a negative x, that is going to be the negative sine of x. So the idea here, if I took the sine of a negative pi over 4, that would be the same thing as the sine of pi over 4, but the opposite sign, S-I-G-N. Okay, so there's kind of my basic identities that have to do with sine. Some basic identities that have to do with cosine, likewise, right? Cosine is 1 over, I'm going to give myself a little bit more room here, 1 over secant. Likewise, secant of x is 1 over cosine, right? Those are just definitions. Remember, an identity is an equation that is true no matter what replacement we put in there. So if I put in an x value, this is going to be true no matter what x is. There's no restriction on what x is for this to be true. Other than like the Pythagorean theorem only works in a case of sides of a hypotenuse, or this for right now only works when we're in the real numbers. So cosine of a negative x, the other one, cosine, remember, is an even function. So when I take the cosine of x, that's the same as cosine of negative x. That's true because cosine, if you think about it, is positive in 1 and 2 and negative in 3 and 4. So if I take, positive in 1 and 4 and negative in 2 and 3. I'm recording this after a long day of work. So cosine, right, if I take the cosine of a negative pi over 4, well, that's in quadrant 4, which is exactly where pi over 4 is. And so they're going to have the same value. Okay, and then let's talk about tangent. Tangent's going to have a couple of them that we maybe haven't actually defined yet. But tangent, of course, if we look at the reciprocal function, is the same as 1 over cotangent. And likewise, cotangent of x, right, is the same as 1 over tangent. And in terms of even or odd functions, actually tangent is odd. Aren't we all kind of odd in one way or the other? Aren't we all like tangent at some point in our lives? Why would you, you don't want to be normal. It's okay to be odd. I'm a math teacher. We're an odd group, okay? So there are my tangent, but there's a couple more things with tangent and cotangent that we actually haven't written down yet, which are going to be quite useful for us. And you may have seen that this is true when we've been dealing with, we know that tangent is y over x in the unit circle. And remember, in the unit circle, our y values, if we think of that unit circle, which I already said, our y values are sine. So we can actually say now that tangent is the sine of x divided by the cosine of x. And this is something that we are going to use constantly, okay? So the tangent is the sine of x over cosine x. Likewise, what would the cotangent be? Well, cotangent is just 1 over tangent. And so I'm just going to flip them good, and I get cosine over sine. So these are kind of the basic identities that we're going to need as we move on. When we're going to get to something called proving identities, which maybe you've heard of in trigonometry, and sometimes one way to go about proving those or simplifying expressions is just to get everything in terms of sine and cosine, and these are the identities that are going to do that for us. Okay, all right, so let's leave those there. We'll come back to this. And let's develop, so the title of this section says the Pythagorean identity, the sum and the difference. So let's talk about the Pythagorean identities. So this is going to kind of come from, I'm going to prove this to you. And notice it's identities, right? But I'm going to talk about kind of the first one, which is always a good place to start, right? With the first one. So I just cracked myself up, but at least I cracked someone up, right? All right, so the Pythagorean identities, I'm going to just prove this to you really quick using a triangle, but we can also use the unit circle. Is much faster to prove this, but I just want you to see this kind of using a triangle. So let's look at, your book just uses the unit circle, which is fine. Let's look at a triangle, ABC. Let's look at theta. And if I look at some things about theta here, so what do I know? I know that the sine of theta, right, the way I have this is b over c, okay? And what do I know? The cosine of theta, right, the way I've written this is a over c. So remember those, when we first started talking about trigonometry, we only talked about sine and cosine of acute angles in a right triangle. Now, of course, this goes to any angle, and now we don't even think of them as angles, we think of them as real numbers. But look what I'm going to do here. So I'm going to solve this really quick. So I'm going to solve this equation for b, and I'm going to put b on the left hand side. So if I solve for b, I get c times the sine of theta, right? Likewise, if I solve for cosine, I'm going to get c times cosine theta equals a, right? Or I didn't say solve, I meant solve for a. And then what else do I know about right triangle? Well, we had already said this before. We know that a squared plus b squared, right, equals c squared. So I'm going to take these guys right here, what I have for a and b, and I'm going to substitute it in for my a here and my b here. So what do I get? Oh, I probably should have had sine ba. It doesn't matter, you guys. Doesn't matter. So I have c times cosine theta, right? Look at what I've done there. I know that a is equal to c times cosine theta. So I just plug that in right here in this triangle. Plus, what is b? B is c times sine of theta equals c squared. If I simplify this a little bit, remember we can distribute. Your math teachers will not freak out at you if you distribute exponents across multiplication or division. When will they freak out on you? Oh, they'll freak out on you if you do that. Oh, my squares across addition or subtraction. So don't do it. All right, I'm going to do a couple things here. So I'm going to factor out a c squared. And then also I'm just going to switch the order. You guys, it doesn't matter. It doesn't matter. We're just used to having the sine first. I think we get used to that because we want to remember tangent is sine over cosine. Anyway, it doesn't matter. But I'm just going to put sine squared first. So all I did was factor that out. And now look at you guys. I divide by c squared. Isn't that cool? And I have this really great, beautiful, just really neat Pythagorean identity. And it's sine squared plus cosine squared equals 1. I'm being a little lazy here. It should be sine of theta squared plus cosine of theta squared equals 1. But you know what I mean. Sine squared plus cosine squared equals 1. You may have heard of this before. You're at a party. People are talking about trig. I mean, that's what you do, right? At a party. And the identity, Pythagorean identity comes up. The other way you can think of this, you guys, is on the unit circle. Oh, Oh, that was really, really bad. But remember, any point on the unit circle, right? So the first value is cosine of s is what they use in your book, and sine of s, right? X is your cosine, y is your sine. And remember that this unit circle is given by x squared plus y squared equals 1. That's the definition of a circle centered at the origin with radius 1. So if my x coordinate, if I'm lying on this circle, that must mean that this x coordinate must satisfy this equation, and this at the same time that the y coordinate does. So notice, what does that give me? Cosine squared of s plus sine squared of s equals 1. And then we're going to replace those s's with x's just to kind of get used to the function notation that we're used to. But we don't want those x's to confuse you right now. So we're going to have just cosine squared plus sine squared equals 1. Isn't that cool? I know. I think it's cool too. Let's write this down a little bit more. Actually, before we write it down, what I'd like to do is just kind of talk about, we have some other Pythagorean identities. So this says if we use kind of function notation with the x's, that sine squared plus cosine squared equals 1. Notice that is not sine plus cosine equals 1. You cannot square root each term. Don't you dare. You do not square root over addition. You do not break up square roots over addition. Sine plus cosine is not 1. Sine squared plus cosine squared is 1. We can actually get some other Pythagorean identities from this identity right here. Remember, this works for everything. So I want to develop those other identities. So the first thing I'm going to do is I'm going to divide everything by cosine squared. I'm going to see what we get. So if I divide everything by cosine squared, what is a resulting identity that comes from that? If I divide everything by cosine squared, I get sine squared over cosine squared. So remember, sine over cosine is tangent. So sine squared over cosine squared will be tangent squared. And then what is cosine squared divided by cosine squared? That's 1. And then 1 over cosine is secant. So what is 1 over cosine squared? You got it. That's secant squared. You guys remember how I told you that tangent and secant are friends? This is what I was talking about. So they are buddies when it comes to the Pythagorean identities. I mean, they're buddies with everyone else too, but you know, they're kind of buddies. And when you get to calculus, you're going to see that they're buddies also. It's really cool. All right, so I divided everything by cosine squared to get that, and this is a trick you can use. So if you should memorize all of them. If you get in a point in a test or a quiz where you're like, I just can't remember the other ones, you have to know sine squared plus cosine squared is 1. To develop the other identities, then just divide everything by one or the other. Divide by sine squared everything, and then divide by cosine squared everything, and you'll get it. So let's divide everything by sine squared and see what we get. So if I divide everything by sine squared, okay, what am I going to get? Now, this identity, right, is true for all of them. So sine squared divided by sine squared is 1. Cosine squared divided by sine squared. So remember, cosine over sine is cotangent. And if I square both of them, then that's cotangent squared. And 1 over sine is cosecant. So 1 over sine squared is cosecant squared. So tangent and secant are friends. Cotangent and cosecant are friends. So let's write these down a little bit more formally. I always have to sound this out. Pythagorean. There we go. So the Pythagorean identities, and then you can do a bunch with these, but let's look at kind of what the Pythagorean identities are going to give us. There are 3 main identities, okay? So we have sine squared x plus cosine squared equals 1. That's one of them. We have tangent squared plus 1. Oh, I need an x in there. Equals secant squared. And then we have 1 plus cotangent squared. I'm going to, let me fit this in a little bit better. Oh yeah, it's a little bit better. That's the power of the pause button and then starting it again. Poof, there you go. All right, I just wanted to kind of break these up because we can actually get some other identities that are kind of cool from this. So sine squared plus cosine squared is equal to 1. Tangent squared plus 1 is equal to secant squared, and 1 plus cotangent squared is equal to cosecant squared. Notice it does not matter if I put the 1 first or not. I could have just as easily said this was cotangent squared plus 1, right? Or here, cosine squared plus sine squared is 1. We know that addition is commutative, so it doesn't matter what order we write addition. Okay, but from this, There's some interesting things. So some other things that are also identities. What if I isolated cosine squared? If I got cosine squared by itself, this identity also implies that cosine squared is equal to 1 minus sine squared. And that's going to be, these are going to be things that you will want to start being able to recognize. Okay, and that sine squared is equal to 1 minus cosine squared. So if you see a 1 minus sine squared, you know that those two terms together equal cosine squared and vice versa. So those are important to remember and important to know. Also over here, I could do the same thing with tangent, right? What if I subtracted that 1, right? So a result of this would be that tangent squared of x equals secant squared of x minus 1. Okay. Or another one that I think is kind of funny is what if I get 1 by itself? 1 equals secant squared minus tangent squared. Okay. These are all results of having this identity. I can rewrite it in different ways. And likewise over here, if I solve for cotangent, cotangent squared, right, will be cosecant squared minus 1. Or if I solve for 1 is equal to cosecant. That one, I'm going to be honest with you, we don't use a whole lot, but it could come up cotangent squared minus 1. Those, again, are all results of those Pythagorean identities. You have to know the Pythagorean identities. You have to know them. You need to buy some flashcards, or you need to write them down a bunch, or as you're watching a movie or something, or a Netflix show, you need to just be writing down these identities. Okay, that's one way I memorize things if I have to memorize things, which I don't have to very much anymore. I'm thankful for that. Is I'll just get a piece of paper and my notebook and just keep writing them down. Okay, so let's do some examples with this. And I know I don't need that, so let's get rid of that. Oh, come on, Sarah. We don't need that. Okay, so some quick examples. So these can be tough. These can be tough because when I ask you to simplify completely, is there an E in there? I don't know. I feel like there might be an E there. Oh no, there's not an E in there. That looks weird, doesn't it? Simplify completely. So what's going to be hard about these is you're not going to know where to stop. But what we want to do is we just want to use all of our identities to see how much we can simplify this expression. And that's really, I know it's not going to seem like it's useful, but it's really, really useful when you get to like calculus. And I'm going to make it useful for you in this class because you're going to get a grade for it. But it's useful because if I can see an expression and be able to simplify it down and I need to do other things with that expression, I've made my life a lot easier. So let's look at something like this. How about, what if I have cosine of x times tangent of x, right, minus secant? And again, this is really a lesson in using these identities and getting comfortable with them. So I have cosine of x times tangent minus secant, and I have a time sign there. So there are a couple ways you can go about doing this when you're looking at simplifying expressions. If you have a fraction, you can try and combine like fractions. If you have everything, and if you have like basically all signs and maybe just one cosine, you could rewrite everything in terms of maybe just the sign. Like I could rewrite cosine squared if I have a squared, right? I could do that. Or for something like this, if I have a tangent and a secant, I could rewrite these in terms of sine and cosine and see how that's going to affect my cosine. Also, I have multiplication. So what I would actually first do if I were to do this one, which, what do you know? I'm going to do this one. I'm going to go ahead and I'm going to multiply that cosine through to each term, and then I'm going to see what can happen after that. So I'm going to take cosine x times tangent of x minus cosine of x times secant of x. Okay, and we know from up here, what do we know tangent is? Tangent is sine over cosine. And what do I know secant is, which we've known for a long time? That is 1 over cosine. So because I have cosine times tangent and cosine times secant, I am going to rewrite tangent, okay, using that identity as sine over cosine. And a lot of times what I'll do is I'll put this over 1. Don't multiply the cosine to the top and the bottom, right? It's just over 1. And then again, this is cosine x over 1. Just because I know I'm doing fraction multiplication, I'm going to put that over 1 so I don't forget that. And now that we've written things in terms of sine and cosine, it's easy to see what's going to happen. So my cosines can cancel here. Notice what am I going to be? I'm going to move over here so I have room down here. I'm just left with sine of x over 1, which is also just known as sine of x. And then here also my cosines cancel, and I'm just left with 1 over 1. That's not 0, so don't just get rid of it. But what is 1 divided by 1? It's just 1. And are we done? Yeah, I think we're done. We just have sine of x minus 1. If that was sine squared of x minus 1, then I could probably do one more step. I could deal with cosine squared somehow, but it's not. So you need to just leave it as sine of x minus 1. Can't really rewrite it in terms of anything. You know, I could rewrite it in terms of cosecant, but that's not going to simplify it more. That's just going to make it more complicated. So we're done. So basically this section is just going to be a lot of examples. What about something like sine squared x times cosine squared of x plus cosine to the 4th? So let's see what's going on here. I don't have sine squared plus cosine squared. If I saw a sine squared plus cosine squared, I would make that 1 right away. I have like sine and cosine, and it's being multiplied by cosine to the 4th. I have a lot of cosines. One thing that I could maybe do is maybe rewrite sine squared as 1 minus cosine squared, but it seems to me like it's not really going to simplify it very much. The key to this one right here is actually going to go backwards from what we did up above. What I want to notice is this guy has a cosine squared on it, this term does, and this one has a cosine squared kind of inside that cosine to the 4th. So what I'm going to do with this one is I'm actually going to factor out a cosine squared, and I'm going to throw up a little prayer to the math gods that something cool is going to happen, and it is, don't worry. So I'm going to take that cosine squared out here. What am I left with? I'm just left with that sine squared of x. If I take cosine squared from cosine to the 4th, right, I'm factoring out 2 of them. Because remember, we add exponents when we multiply like bases, and we subtract exponents when we divide, and factoring is just dividing. So I saw that I had a cosine squared in each term. I factored that cosine squared out. You guys, ding, 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 ding. What is this right here? Yes, I'm imagining you're yelling it out. Sarah, it's 1. It is 1. Sine squared plus cosine squared. My friends, are we friends? I think so. It's 1. So I have 1 times cosine squared. So this whole thing here simplifies to just cosine squared. And if you wanted to write that cosine squared as 1 minus sine squared, you sure could. I would probably just leave it like that. Rewriting it as 1 minus sine squared doesn't seem to really simplify it more to me, right? It gives me more terms, and it doesn't seem more simple than cosine squared itself. And that's it. That's as much as we can simplify it. And there's not a whole lot more we can do with that. Remember, when you're doing these expressions, you don't have them set equal to anything. So one thing you can't do is you can't say like, oh, I'm going to multiply everything by cosine. Oh, I'm going to multiply everything by 4 to get rid of the fraction. You can't do that because you don't have it set equal to anything. When I put these equal signs, those equal signs are really to just tell my reader that I'm taking this guy right here and I'm starting the simplification process. And this equal sign is telling me that here is what I've done to equal that expression right there. So please be mindful of that. You cannot multiply everything by something because we don't have an equation. When we have an equation, then I can do that. Don't worry, we'll get there. We'll get there. What about cotangent of theta divided by cosecant of theta? All right, guys, so neither one of them are squared, so I can't use the Pythagorean identity. I can't square the top and square the bottom. You cannot do that. And when I say these things, you're like, Sarah, why would anyone do that? It's because I've seen it. I've seen a lot of things in my life as a math teacher, and that's one of them. So, let's look at cotangent. So cotangent over cosecant. I don't know what to do with this. I mean, I do know what to do with this, but when in doubt, right? When you're not quite sure how these guys are related, rewrite everything in terms of sine and cosine. So if we look back to my basic identities, what is cotangent? Cotangent is cosine over sine. So I'm going to rewrite everything in terms of cosine and sine and see what happens. So cotangent is cosine of x all over sine of x, right? That is what cotangent is. And then what is cosecant? Cosecant is 1 over sine of x, okay? So now I can see some stuff that's going to happen. I have 2 fractions divided by each other. So I'm going to take cosine over sine. I'm going to flip the denominator and multiply. So if I flip 1 over sine, it becomes sine over 1. And then you can see my sines cancel out. And what does this whole thing just simplify to? It just simplifies to cosine. And that's it. Isn't that great? Let's do a few more. I like doing these. Part D. Let's simplify 2 sine squared of t. I won't have to have x's. Plus sine of t minus 3 all over 1 minus cosine squared of t minus sine of t. Oh my goodness. This is crazy. 2 sine squared plus sine of t minus 3 all over, that looks like cosine of 2t. That is not cosine of 2t. That is cosine squared of t. Okay, I'm just going to show you how to do this one because it's tricky to see it. What I want you to do is notice if I took these signs right here, whoa, and I replace those signs, let's say with like the letter M. Okay, I don't know why I'm choosing M, just for something different. Do you see how if I just replaced those with M, the numerator becomes 2m squared plus m minus 3. Just replacing that sine of t with m. And guys, this looks like something that we've had drilled into our heads that we should factor. And you know what? It does factor. So I'm going to factor this guy, and then I'm going to replace those m's with the signs. Hopefully you'll get to a point where you can do this without having to do the m trick. But if you aren't quite sure what's going to happen here, because the thing is I have a sine squared and I have a plain sine. I don't have a sine squared on top. If they were both sine squares, I might be able to do something. Or you guys, even if this was a cosine squared, I might be able to rewrite that cosine squared right there as 1 minus sine squared and then get some stuff going on. But I don't. That guy is not a cosine squared or a sine squared. So I'm pretty much forced to maybe try something like this. So I need a positive 3 and a negative 2 for this to factor. And so what I've done, I've factored the numerator into something that looks like this. And instead of m's, I'm just going to put sines. FOIL it out. I'm not going to do that right here for you because then we're already at 26 minutes and we still have a couple more identities to get to. But I would say FOIL that out. Verify, but don't just take my word for it. You know, make sure that you believe in it. And then here, okay, so look at we have an issue, right? On the bottom, I have a cosine squared. We can't have a cosine squared, guys. Everything's in terms of sine. But notice if I kind of group this, which I can put these parentheses because this isn't multiplication, and it doesn't imply multiplication if I put it there, I suppose I should say. What is 1 minus cosine squared? 1 minus cosine squared is sine squared. So that's one of those kind of consequences of our Pythagorean identities, right? That cosine squared is 1 minus sine squared. So now that I've done that, notice how I have everything in terms of sine. And so I'm going to just keep the top in this really beautiful, don't you think, factored form. The other reason this stuff is going to be important is we are eventually going to solve equations that involve trig functions. And it'll be important to be able to simplify. In the denominator, because I factored the numerator, let's factor the denominator. I can take a sine out, right? If I take sine squared and divide it by sine, I just get sine. Sine divided by sine is 1, okay? And so we did all that work and we got rewarded a bit. That cancels. And so I get 2 sine of t plus 3 all over sine of t. Now, I'm not quite done. I want things to simplify. I want things completely simplified. So while this looks this looks pretty, there's a couple more things we could do to this. So I could take, don't you dare cancel those signs. Don't do it. I know you were about to. Don't. You can't. You guys, that 3 up there, because it was addition in between the 2 terms on the top, that sign is dividing both of them. So don't you dare cancel those signs. Now that I have divided each term by sine, so I've divided this term by sine and I've divided this term by sine, now I can cancel because that's multiplication right there. So I just get 2. And here, you guys, what is this? This is 3 times 1 over sine. But what is 1 over sine? It's cosecant. So do you see how this really is the simplified form? This was all right, but this one right here is really nice and simplified. And then you get to cancel that sign, which I know you wanted to do. Let's do one more. I really like doing these. All right, so number 5. Okay, so we have cosine of x all over 1 plus sine of x, okay, plus tangent. And it looks like I'm probably going to make this lecture 2 sections because we still have to talk about the sum and difference identities, and I would really like to prove those for you, and I feel like if I do that in one lecture, might be too much. Okay, so we're going to do 2. So, but let's look at this, something like this. Cosine over 1 plus sine of x plus tangent. You know, I think what I'm going to go ahead and do is I'm going to rewrite tangent in terms of sine and cosine. I actually just have this in my notes and I actually haven't worked it out. So let's hope that something cool happens because I'm not exactly sure what this is supposed to simplify to. But I know that this guy right here, I can't get this into tangent or cotangent or anything. So I'm going to just go ahead and rewrite tangent as sine of x over cosine of x. And then because I have 2 fractions, I might as well try and put them together and see if something cool happens in the top. So I'm going to get a common denominator. So my common denominator is just those 2 denominators multiplied together because they don't have any factors in common. So this fraction right here is going to get a 1 plus sine over 1 plus sine. This fraction over here is going to get a cosine x over cosine x. And my notation is has much to be desired here, but all right. So what do I get for this one? I get cosine squared. What am I going to get here? Well, let's just put sine of x times 1 plus sine of x. And then, you know, on the bottom, you guys, I'm just going to leave it in factored form. If maybe that was 1 plus cosine on the bottom, I would maybe multiply that through to try and get a sine or a cosine squared. Or if I could somehow get a sine squared, cosine squared on the bottom, I might FOIL it through. But for right now, I don't think I'm going to get anything like that. So I'm going to leave it in factored form in the hopes of maybe that cosine of x will cancel, or maybe 1 plus sine of x will cancel. So let's see what happens on the top. So I'm left with cosine squared. I'm going to take that sine through. So I'm going to have plus sine of x, take the sine through to the other one, and then I get plus sine squared of x. Yeah, this is going to be good. All over cosine of x times 1 plus sine of x, okay? You guys, look at what we have. I have a cosine squared plus sine squared. You have to start recognizing those. I'm not saying you're going to start recognizing that today. That's unrealistic. But the more you practice these, the more you work with them, the more you're going to see that that is true. Again, leaving the denominator in factored form because if I multiplied that through, I would not get like a sine squared or a cosine squared. Okay, you guys, ding, 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 ding. This guy right here, what is that equal to? That is correct. That is equal to 1. So I get 1 plus sine of x. I'm going to have to do some funny stuff and go like up here, but that's all right. That's all right. It's okay. I can be totally cool with that. I'm not like super weird about notation and stuff. I'm like totally free with it, man. All right, so 1 plus sine of x, those guys are going to cancel. Now, what do you get on the top? You get a 1. Remember that cosine doesn't magically float to the top because you canceled those 2. So what are we going to get? This is going to equal, I don't like my equal sign like that. We're just going to move up here. We'll just do an arrow to say that. This is going to equal 1 over cosine of x. And then I'm not going to leave it like that. What is 1 over cosine of x? That is secant. Look at that, you guys. This whole thing right here is equivalent to secant of x. If I were to use something like this, I would much rather deal with something like secant of x than this cosine of x over 1 plus sine x plus tangent of x. Yeah, it took me a while to get there, but if I'm going to be, a lot of times in calculus, we'll use a function like this over and over, or if I'm going to go to take the derivative of it, I'm going to have some serious rules happening here that can be quite complicated. And so if I can simplify it down to this secant of x, it's super easy. All right, you guys, so practice doing these simplifying these expressions. I have a feeling that quite a few of these next sections will be broken into 2 parts just because I want to do a lot of examples for you. That's how you're going to get good at these. You need to watch these videos all the way through. Obviously, if you hear this, you've done so, but you really need to make sure you're watching these examples because that's how you get good at this. All right, stay tuned for the second part and have fun.